Excellent. Excellent. Point. There we go.
Hey. I can throw things back at you now.
Bring the camera. Okay. Come on, there's still people coming in, so just pull up. 2 minutes before 6:50.
There's no other talk.
I'm going to go drag more people on the camera.
Ollie. Pardon? We had lots of people coming over to our booth and asking us for short demos from Backtrack to the Mac, so I'd like to give a huge hands to the Shmoo group who managed to organize all of this in absolutely no time, and they made this thing possible, so please. Really, thanks a lot. Thanks a lot. It really is appreciated. Saying this, I had 12 minutes to prepare my demonstration. So if anything goes wrong, Chris is over there. Stand up, please, Chris. Please. So if anything goes wrong, he's the guy to nail. Okay. And if it's not his fault, then it's Windows. Okay.
My email address is must.
All right. So. We'll be looking at 2 demonstrations today. Both of them are just Ollie games, basically, debugger games. Yeah. Damn Microsoft. So the first demonstration is going to be, it's actually a nice demonstration. We're going to be bypassing a sort of low-level antivirus system with Ollie debug. We'll be encrypting or encoding a file. And then if we have time, and if you have patience, then we'll be going through the MS-07017 vulnerability, and we'll be exploiting it under Vista. And we'll be exploring the ASLR protections and its bypass, obviously. All right, so we'll begin with the antivirus avoidance spiel. And basically, if we talk about your classic antivirus, I'm not talking about all these fancy heuristics things, which I don't really believe in, but basically they're signature-based. So when you have malware, if you have your binary file, then the specific bytes in a specific area will actually trigger a signature. And these are files on disk. So that's basically what the antivirus does. It just goes through the files and looks for signatures. So basically, if we want to bypass an antivirus, what we need to do is we need to change the file's signature without changing the file's functionality. So this is generally what we'll be doing. We'll be doing this in an interesting sort of way. I mean, the trick itself is pretty old, but the implementation using Ollie is fascinating in my opinion. And what we'll be doing is we'll be hijacking the execution flow of the executable, and we'll be injecting a small stub, a small encoder stub somewhere in the file. And what this encoder stub will be doing is it will just change the binary contents of the file, and then once we execute that file again, it will decode the encoded contents of the file, but it will be doing this in memory out of the reach of the antivirus. And hopefully that should be enough to fool this poor antivirus we'll be demonstrating it on. We'll be using XOR. What's the proper way of saying that? XOR, which is a simple sort of routine which, if you implement the same XOR with the same key on the same data twice, then you'll actually be reverting back to the original contents. So that's sort of simple and nice to present, but you'd probably find that with more advanced antivirus software, an encryption, or it's not really an encryption scheme, it's a decoding scheme or an encoding scheme like this won't really hold. But we'll be doing sort of a basic demonstration just to show the impact. Alrighty, so let's see what we've got here. This is sort of a graphical explanation of what I'll be trying to do. I always find it easier to understand things in pictures. So if this is our malware, which we'll be starting with, and let's say this is the part in the file that the signature is at, and the antivirus gets ticked off by that, then basically what we want to do is we want to change the entry point of the file into some other place, have our stub there, and have it encode all that section, and then we'll freeze the file. And then when we run it once again, the same stub will decode that section of the PE file. Okay, so let's get dirty and see how this actually works. Well, not dirty in that sense, but you know what I mean. Alrighty, so I downloaded sort of one of the oldest backdoors in existence. Do you remember this? It's like the Netcat auto bind shell on port 99. If you double click on it, which you're not supposed to, you're supposed to run it from console, what it actually does is open a listening port on port 99, and it binds a command prompt to that. So if anyone telnets to this machine on port 99, they'll actually get a command prompt on my machine. Okay, so this is a really, really basic Trojan horse, if you like. It's just like my proof of concept, which I'll be demonstrating this stuff on. Alrighty. So let's just check that my poor antivirus actually identifies this file as malware, which it should. And if we inspect the antivirus, what was that thing? Here it is. So we can actually see that the antivirus has identified this file as Trojan backdoor NCX something or other. Okay, and that's probably because there's a signature somewhere in that file which is known to the antivirus vendors. So let's start looking at this file and see how we can change it, or change the binary structure of the file without changing its functionality. All right. So the first thing I'd usually want to do in a situation like this is open the file in a PE editor and prepare it for my stub. So we'll just use load PE, and we'll load this file, and we'll look at the various sections that it has. Now, the stub itself is pretty small. We could probably fit it in less than 100 bytes, but I usually like to overkill in these situations and give myself a lot of room for these manipulations. So what I'll be doing is I'll be adding 1,000 bytes to the iData section of this file, and I'll be doing all my stub thing in that area. Okay, so I'll quickly add 1,000 hex bytes to this file, and I'll make sure that it has executable permissions, because our stub is going to be in there and we'll have to execute code. So I'll do that quickly, and then when I was testing this yesterday, I realized that I also need to make the text section writable, because we're going to be encoding and decoding stuff in the text section. Okay, so we just need to make sure that this thing has writable permission. So now that we've done that, we've changed the PE file structure. In most probability, this file will actually not work, because the PE section says that it's bigger than what it is on physical disk. So in order to get this file back up and running, we'd probably need to pad it with 1,000 hex bytes. So I'll quickly do that. And I'll just add 1,000. Okay, so that basically just padded the file with a lot of space for me to work in. I'll save it, and hopefully this file should regain functionality. Ah. Yeah, blame Microsoft. Chris or Microsoft, one of the two. No, it's my laptop. It'll probably take a few seconds just to pull out of this. Okay, so there you go. It's functioning. It's probably open port 99 and waiting for all the evil hackers to telnet back into my machine. Okay? Okay, so what we did until now doesn't really help us in avoiding antivirus software because we haven't really changed anything apart from just adding padding to the end of the file. So it's still identified as malware. But let's start our Ollie games now and see what we can actually do in order to encode and decode this file in real time. So we'll open wonderful, wonderful Ollie. Actually, I should be using Immunity Debugger because it's like, you know, light years ahead. But I find that Ollie has a much smaller footprint, and for simple demonstrations, I still prefer using it. But if you want to do this, you really should download Immunity Debugger. It's light years ahead. Okay. So we open our malicious file, and Ollie takes us straight to the entry point of the file. Okay, and these are basically the first instructions to be executed by the file. And what we want to do is hijack the execution flow and redirect it to an area where we can actually inject our stub. So just to be organized, I'll copy-paste this stuff which I'll be overwriting, and I'll put it in a nice notepad file, in a text file. Okay, we'll be using these addresses and these commands later on for reference. And what I'll say, what I'll look for now is that iData section which we enlarged. And you can actually see that these are all the bytes that we added, yeah? So if I were to choose, say, this address to inject my stub, that actually looks good. So let's make a note of this. Let's say code cave starts at, and what is that? 0041, what was it? 41? 2800, thank you. Yeah, that looks good. And let's start our hijack. So I'll go back to the beginning of the file. This is, once again, the entry point. And I'll overwrite this stuff with a jump directly to our new code cave. Okay, so I'll overwrite this, and I'll say, please jump to my code cave. And when I do this, you'll actually see that these first few instructions will be overwritten. Okay, let's just look at that, and you'll see that I overwrote these three instructions. So I'll save this change to file. You can do that through Ollie. I always get confused here. Save. No. Save to, yeah, there you go. So I'll save that change, and we'll save this to a new file called -1. So let's open this new file in Ollie and see what happens. All right, so once again, we're taken to the original entry point. We can see that our command was rewritten. And if I single-step this command, I'm taken straight to my code cave. Yeah, that wonderful place where I'll be doing all my evil stuff. So now that I'm here, what I want to do is I want to add my XOR loop, which will decode and encode the file each time it's executed. So I've actually got in the presentation Let me show you this. It's much easier than it seems. All right, so this is our loop. And basically what we're going to be doing is we'll be encoding part of our file. I'll be encoding just the data section of our file, because that's enough for this demonstration. And I'll be starting the encoding routine from a specific address, which we'll identify in a few seconds. And I'll be moving that address to EAX. I'll be XORing the contents of EAX, and then increasing EAX, and then comparing it to the end address that we want to encode and decode at the end. If that address has not been reached, then the loop just goes back to the XOR routine, and it continues that way until we actually reach the end of the section that we want to encode and decode. So that's basically the loop. So let's quickly do that. I'll literally copy-paste this information. Perhaps before I do that, I'll just identify what sections I want to encode and decode in the file. So let's go back. And my guess is if we start encoding our file from this address, and we run all the way down the data section, this looks like a good ending point. Then we should be okay. All right. So I'll grab my encoder, which I've already got here. I'll just make sure that the address is okay, so it'll be easy for me to copy and paste, because we're under serious time restrictions. Is this loop clear to everyone? I mean, assembly looks scary until you actually try it. All right. So we've jumped. Let me just restart this so I don't make any mistakes. And this is our code cave, so I'll just start pasting in my encoder. No, I think I made a mistake, actually. Good thing that I caught this. So it's going to move that to that address, XOR it, increase it, compare it. And if it's not equal, we actually want to jump back to the XOR routine, which is at 412805. All right. So this is the routine that's going to encode and decode the whole file. And once the whole file is encoded, what we want to do is we want to reintroduce the commands that we overwrote with our initial hijack. So let's quickly do that. And then once we've introduced these instructions, what we want to do is jump back to the original place where we left off after our hijack. So that should be this address. So we'll just jump there. And I hope I haven't made any mistakes, because it will be very embarrassing if I have. And we'll save this to disk. And let's see this file run under Ollie now. Okay, so once again, our execution flow is hijacked by the initial jump. We've got our encoder scheme here. Now, let's take a quick look at how this works. I'll I'll actually go to this address. And this is basically the binary contents of the file. Okay, if we look at it in the disassembly, we'll see exactly where we left off in the top window. And I'll start the encoder, which is also our decoder. So we've moved the starting point of our encoding address to EAX. We saw the contents, so look at this area here. See that byte changed. We're increasing EAX. We're comparing it to the last section that we want to encode to. Since it hasn't arrived, we're jumping back to the SOR loop, and this is going to continue. And you can actually see the file being encoded as we speak. So obviously, I won't do this manually. I'll just put a breakpoint here. And when I let Ollie run, you'll just see all of this change really, really quickly. There you go. So basically what we have now is a file which has a stub and garbage in the data section. Okay? What I need to do now is take a snapshot of this file as is and save it to disk. And the next time that this file will be run, the same stub will run the same XOR loop on all the data section and will actually bring it back to the original file contents. But this will happen in memory and not in disk. So the antivirus will actually have nothing to say about this. Okay, let's try this. This is actually the annoying bit. Let me make sure I don't make any mistakes here. All right, so I'll be saving. Notice that all the commands are really gibberish now. They do not resemble anything that we've seen before. And what I'm going to do now, and this is a bit tedious, I have to actually select the whole data section to copy and paste it. I can't actually press Control-A. So I sort of have to think of something to say to entertain you while this happens. So Chris, go ahead. Nothing? Save me!
Take your top off. Was that relic? Was that relic? Or was that zero chaos?
Zero chaos, and you didn't even see him.
Yeah. Too short. If it was relic, you'd be like, no, that's fine. Thanks, relic.
All right. So this is the end of our file. I'll just make sure I save all of this. Copy to executable, and we'll save this to number 3. So once again, this file on disk, at least the data section, is garbage. But once we run this, execution flow will be redirected to our stub. Our stub will decode the encoded data section and then execute normally in memory, hopefully. Let's double click this and see if we actually get a shell on port 99. Please don't crash. No, wrong one. Wrong one, thank you. Looks promising. Oops. All right, so the file is actually functional. Question is, not yet, thank you, not yet. I told him, listen, you got to support me when I go up there. You got to clap, but you have to clap at the right moment, so. Thanks anyway, okay? Okay, so the big question is, what will happen now? Alrighty, okay? All right, so that's quite nice, and I actually have an excellent slide here.
You just made half the room's job harder.
Thank you, thank you, thank you. Are we good with time?
You are great with time.
Okay. So, second demonstration, ADD sucks. It does, because I made this demonstration and I couldn't find it for like 2 hours on my hard disk. Okay, so the next demonstration is an awesome demonstration, which I really, really love. And this is actually in reenactment of the MS-07017 vulnerability, the infamous Annie exploit thing. But there's an interesting angle. There's an interesting angle when you try to exploit this on Windows Vista. And this is what I'd like to do now. So you've got all the determiner vulnerability reports. There's sort of like the basic stuff is over there. I've actually got the vulnerability report itself. It's an interesting read. If this interests you, then take a look at it. And they've got a really, really interesting write-up about it. So the day this came out, well, not the day actually, it was like a couple of weeks later, I was looking at it, and they've actually got a proof of concept here, which shows the file structure which will trigger the overflow. So we'll be copying this, and we'll be working on the POC, and we'll be trying to get a bind or reverse shell. It doesn't really matter. As long as we get some sort of code execution, then we've done our part. If you want to put evil shellcode in, go ahead. Now, obviously, this thing has been patched since 2007. When was it? August? But again, the exploitation process is astounding, in my opinion. The whole process of bypassing ASLR was just brilliant. So this is what I'd like to show you now. To save some time, I've created my Annie files ahead of time, just so I won't have to mess around with Notepad too much. And basically, what we have here... Wow, I'm freezing. Excuse me. Basically, what we have here is an Annie file, which has got the exact same structure as our proof of concept. Let me just verify this. Yeah. So we quickly build an HTML file, which we'll call this malicious Annie file. Let me just make sure that everything's good to go here, because obviously 3 seconds before the demonstration, everything crapped up on me. All right. So if we double-click this, we can close this, and we can close this. If we double-click our proof of concept, and shove it under Ollie, and then refresh this page, we'll actually see that we've got a wonderful EIP overwrite. And basically taking this a step further and getting code execution on Windows XP or Windows 2000 is pretty trivial. But in Windows Vista, you've got ASLR taking control of the whole situation. And basically what that means is that we can't actually jump to somewhere in our buffer, to jump ESP or somewhere, because the base address of all the core DLLs in Windows Vista will change after each reboot. I think I have a let me just see. Yeah. Okay, so this is a demonstration. I actually rebooted Vista between the first screenshot and the second screenshot, and I looked at the same code in NTDLL. And what you'll see here is that at the first reboot, this code was at 776516A1. and on the second reboot, it was at a slightly different address. So this is what ASLR actually does. It randomizes the base addresses of the DLLs. But if you look closely, you'll see that it's only the first 2 bytes which are randomized. Okay, if you look at, I don't know, take something random from there, at this jump, then you'll see that in this situation, the last 2 bytes are 16A1, and it's going to be exactly the same here. So this genius guy says, okay, so let's try a 2-byte overwrite of the EIP. And let's see what that actually does, because it's really interesting. So what we'll do is we'll change the proof of concept to give us not a 4-byte overwrite of EIP, but a 2-byte overwrite. So what we'll do is we'll shorten the ANI header structure by 2 bytes. So rather than having 58 here, we'll type 56. And here, let's just put some breakpoints for now. Pardon me. All right, so let's see what happens when I crash Internet Explorer now. Great. So this is our 2-byte overwrite. Now the question is, how does this actually help us? You'll see that the crash happens in user32.dll, and we can't have our relative jumps in any DLL, let alone user32, because once again, those addresses will be changed each and every time. So what was done here was a really, really interesting thing. Some genius said, okay, let's look for, sorry, before that, where do we jump to? So this is also interesting. Look at this. If we look at EBX, and we'll look at the address that is held in EBX, we'll actually see that we're pointed to the beginning of our ANI header. So a jump to EBX, the pointer, not the register, will take us to the beginning of the file. And this is what we'll have to deal with when we then want to start executing our shellcode. So jump to pointer EBX, that's where we want to go. So if we could find a jump to pointer EBX in user32.dll, we could probably use a partial overwrite to get to that address, no matter where it is located in memory. And that's like the genius step that was taken to bypass ASLR. Okay, so let's take a look at this. Let's see if we can find an address that will suit our purposes. Yeah, find user32.dll in here and I'll give you a free Coke. Thank you, yes, thank you.
The whole room there, but
Okay, so this is user32.dll, and we will be looking for a jump to pointer EBX command. And thankfully, we've got a few. Not good, not good, not good, not good. Good, but I don't like. Not good, excellent. Okay, so we've got a jump to pointer EBX right here. And this is in user32.dll. Now look at the address. Okay? The first half of this address will be randomized on the next reboot. The second half of the address won't. But that doesn't really matter because since we're crashing within user32.dll, if we do a partial overwrite, we'll always be in user32.dll when the overwrite happens, if that makes sense.
Sure.
Okay. So, now we need to start playing with our ANI file and see how we can manipulate code execution into this overflow. So let's try and do that. I'll close this. And I'll say, okay, this is where we have our partial overwrite of EIP. So what I want to have is these last bytes overwriting EIP which is currently pointing to user32.dll. And I will do this, little endian, gosh, I hate this, AB7B, I think. Yes, AB7B. Okay, so this should actually bring us to that jump to pointer EBX location in user32.dll. And if you remember, that will actually bring us to the beginning of the RIF header. So classically, what I'd like to do now is fill this with NOPs or just stick my shellcode here. But obviously, this will damage the ANI file format. So I can't really do that. I can't just go shoving my shellcode everywhere because then, you know, Windows won't recognize this as an ANI file. So here, what was actually done was really interesting because they had to work through the ANI file structure and not break it, and then find a way to get to the shellcode. Okay, so let's see how that works. Obviously, we can't overwrite any of these instructions, which is a bit problematic because we're going to land there. But fortunately, or unfortunately, depends on which side of the fence you're on, these instructions will not damage our stack in such a way that will prevent us from executing our code. So let's just put a couple of breakpoints right here and see what happens when we run this file under a debugger. All right, so once again, double-click, shove it under Ollie. And this time, what I'll do is I'll put a breakpoint on our return address, and we'll see if it actually lands there as expected.
Can you increase the font size?
No. Sorry, I'm sorry. Okay, so let's try and get to user32.dll. User32.dll. It's still not there. This is a bug in Ollie which I never really figured out yet. And we want to look for our return address, which is here. Okay, so I'll put a breakpoint here, and we'll refresh the page, and we'll see if we actually land there. If we have, then we did well, and we've bypassed ASLR. So refresh, and we've got Ollie is actually broken exactly at that point. That means we've hit our jump. And just to remind you, EBX holds the address which holds the beginning of our ANI file. So let's jump. Let's take this jump. And once again, I just want to show you this. We'll follow in dump. And I'll disassemble this. And you can actually see that the instructions here are exactly the same as the instructions here. And this is indeed the beginning of our ANI file. So we'll execute the RIFF equivalent commands. And as you can see, these commands aren't detrimental to our stack, which is good for me. So F7, 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 and I've hit my breakpoints. So this is like minimal code execution, which is good, but we still don't have our shell. So after looking at the ANI file format, they actually realized that they can shove their shellcode at the end of the file without damaging the file itself. Problem is, we can't jump so far. We can't jump from here all the way down here because we don't have enough space to put these instructions. We just have 2 bytes. And we can't push a short jump further than, like, what is it, 128 bytes. So we need to find another place to sort of hop into in order to be able to get to our shellcode. Okay? And as it happens, there are another couple of bytes in this file which we can safely overwrite. And these bytes end up being here. So what we'll actually do is we'll replace these breakpoints with a short jump to here. So we'll just shove in a short jump there. I think it's 22 bytes, which translates to EB16. And we'll put our new breakpoints here. And while I'm at it, I'd just like to put some reverse shellcode. I'd usually do this all in Backtrack, but I didn't really have time to set everything up. So I'll do this the poor man's way. I'll just get this shellcode and I'll remove all the stuff I don't need. I mean, there's thousands of better ways of doing this. Please excuse me. Okay, so this is a, what shellcode is this? This is a reverse shellcode. So let me just make sure that I've got my Backtrack machine up. No. Yes. Okay, so that'll work for this demo. And what I'll do is I'll basically copy-paste this reverse shellcode into my Annie file, and I'll just shove it right here. All right. And let's try running this file once again under a debugger, and I think this will be the last iteration before we get our code execution. But let's just see that everything's working as expected. Obviously it won't. Okay, that's good. And once again, we'll put our breakpoint in our jump to pointer EBX so we can see the code execution happening live. So use the 32.dll. Nope. And refresh. So once again, we've stopped at our breakpoint. We jump to EBX, we execute the RIFF instructions, and this is our short jump to our new breakpoint. And fortunately, from here to get down to our shellcode is manageable. It's like 79 hex, which is just at the edge of the limit, which is just everything I need to get code execution. So we'll replace the second breakpoint with another short jump, and breakpoint. And I think that an EB79 should probably bring me around here. Okay, so I lied. It wasn't the last iteration. There'll be another one. But let's just check that everything's running. And once again, we'll shove our breakpoint. And refresh, and follow the execution flow. All right, so this is our second jump, which should bring us, excellent, to this breakpoint. Okay, and then if we continue, now we're actually executing our reverse shell. So let's fill those breakpoints. Let's remove those breakpoints and get our NOPs in there. And let me just check what this shellcode actually does, because I honestly don't remember. Don't laugh. All right, so it's a reverse shell on port 4321 to this IP address. So I'll just get my Backtrack machine listening on that port. So that's NC minus LVP on 4321. And with any luck, the poor twat double-clicking this file, it's this one. Speaking of the poor twat, should actually send us a reverse shell. Excellent. Excellent. This wasn't my work, I'm just reenacting it. So once again, guys, thank you very much for coming. Thanks for the support, and hope to see you in Vegas.
Not only did you do awesome, you did it in 45 minutes.
Cool.
You did it in 43 minutes.
Cool.
Good job, Buzz.
Thank you. Thank you. Thank you. Thank you very much. Thanks.